Midterm3. Driscoll's algorithm. Prim's algorithm. Topological sorting. Dijkstra's algorithm. The max flow. And Floyd. So any of those you should be able to do by hand. And in terms of like big picture items or like the true false, well, you still need to know all of those. Questions about dynamic programming. Graphs. And greedy algorithm. Okay. Yeah.
Do we need to know like the running time of those?
Like true false.
Okay, so yeah.
But we didn't cover running time for all of them. Yeah, I guess we didn't. Did we? I don't think we spent much time on that. Except for the only one we analyzed was Driscoll and Prim. But all of the running times are in the notes, so it could be in the true false. So, I mean, the exam is only 1 hour long, so I won't be able to ask you all of these. I'll have to pick a subset, but I won't tell you which one I'll pick. You have to be ready for all of them. Yeah.
In the notes, it said there were situations where the greedy algorithm for Maxwell would fail. What would that be like?
I don't know.
Okay.
But the algorithm described is not greedy, right?
I can't remember.
Yeah. For which one? For Maxwell?
I think so.
I don't know. Let me answer that. So in the problem I give you, I expect you to do the algorithm we did in class. You do Dijkstra, you add a weight to all the edges in that shortest path, then your residual path is now altered, now you do Dijkstra again, and you just keep doing it until you're done. And
so like for the final answer for the max flow problem, is it just like the flow chart, or is it?
yes.
What's the maximum number of vertices you'd give us for Maxwell? Because that took me like an hour. The homework one took me like an hour.
How many vertices is in the homework one?
11.
Yeah, I was thinking something like 6 or 7.
Okay, you know what?
But I have to test run it first. If it takes me more than 10 minutes, then it's too many vertices. So I test run it, and then I multiply by 4. And if it's under an hour,
You should multiply by 6.
multiply by 6. I test run the whole test, then multiply by 4. Any other questions? So the one in the homework is 11 vertices. Well, yeah, that's a lot.
Yeah.
Yeah, but 6 shouldn't be too bad, because at some point you don't even have to keep doing Dijkstra. Once the graph is small enough, you can just eyeball it. But you do have to show your work. You just get the answer correct at the end is not good enough. Because I'm testing whether you know the algorithm or not. So that's especially important for Floyd. You have to use all the intermediate matrices. What do you want to review?
Reduce market for Dexter.
Bangstra? Sure. Do you have one in mind? No? Okay. Just make up a draft then. Let's do this graph, and let's find all the distances from A. Oh. Okay, maybe let's add more things. Right, let's do this graph. Okay, so let's do Dijkstra from A. Okay, so you give each vertex the value of the distance from A to there. Okay, so there's an edge from A to B that's worth 3, there's an edge from A to C that's worth 4, edge from A to D that's worth 8, edge from A to E that's worth 7, there's no edge from A to F. Let's add one more arrow here just to make it a bit more interesting. Let's do that. So then out of all these numbers, you grab the smallest one. So that would be 3. Well, technically you should write a 0 there, whatever. So 3 is the smallest one. And then now we scan from B. So from B to C, you could get 5 plus 3 is 8. That is bigger than 4, so you keep the 4. 3 plus 2 is 5. 5 is smaller than 8, so you replace 8 with 5. And those are the only 2 edges coming out of B. So those are the updates we make. So now we look again at the numbers, and of the numbers left, the smallest one is 4. Now you scan from C. From C there's only one edge, which goes from C to F. And 4 plus 9 is 13, so this is updated to 13. Now we look at the numbers again. This is the smallest one. From D, the only edge coming out is DE. And 5 plus 1 is less than 7, so this is updated to 5 plus 1. Now we look at the numbers left, 6 and 13. 6 is smaller. So we scan from E, 6 plus 3, 9 is less than 13, so that is replaced with 9. So the output is that these numbers represent the distances from A to there, right? So from A to B, the distance is 3. From A to D, the distance is 5. From A to E, the distance is 6. From A to C, the distance is 4. And from A to F, the distance is 9. Now technically Dijkstra's algorithm also keeps track of what the path is. Because the graphs are small enough, you can remember the path yourself. So with that drawing, you don't keep track of the paths. If you really implement the algorithm in a computer, you want to keep track of the paths. Here the path is just A to B. Here the path is A to B to D. Here the path is A to B to D to E. Here the path is A to C. And here the path is, oh wow, A, B, D, E, F. So the shortest path, the shortest in terms of way to get from A to F is to go first to B, then down to D, then to E, then to F. Okay? So now if you're thinking in max flow terms, if this is the source and that's the sink, then the path you would take is this long path. Again, Dijkstra, we're done with Dijkstra here. So I'm just now thinking about max flow. You're doing max flow, and that's the sink and that's the source. And the first step is doing this Dijkstra algorithm to figure out this path. And then in that path, you get the smallest number, and then you add 1 to all those edges. So in your flow graph. The flow graph is A, B, E, B, F, C, F. We're also over here, here to there. Oh, I guess I didn't scan from here to there, but 6 plus 2 is bigger than 3, so it didn't matter.
There's also one from A to C.
Yeah, so at the beginning this is just all zeros. After you do Dijkstra, they become all ones. And the rest are still zeros. And now you subtract 1 from each one of these. So this becomes 2. This becomes 1. That becomes 0. That becomes 2. So now you have a graph. And you want to get from A to F. But you no longer have this. So the shortest path is probably 7 plus 2. So then, well, it is 7 plus 2, because 4 plus 9 is too big. So 7 plus 2 is the next one. 2 is smaller than 7. So then, in the next stage of your max flow, you put a 2 here, and you add 2 there. You subtract 2 from here. This becomes 0. Now there's no way to get F through here, so you have to get through F through there. And then the shortest path, probably 4, 9. And then 4 is the smallest number, so this becomes a 4. And that becomes a 4. This becomes 0. That becomes 5. So now there's no edge from here to there. So you have to arrive from over here. So then the shortest path is 2, 5. 5, 2 is the smallest number. So you add a 2 to everything. And then, so this disappeared. this disappeared. So you have to get to F some other way, so the path is A to E, then E to B, then B to C. So you have to do this, and then the smallest number there is this 2. And we add it to here. We hadn't used that one, had we? Maybe we had. So there's 4, we add 2 there, we add 2 here, we add 2 there. And then, I mean, I did this quickly, so there might be mistakes, but I think this works out. So this would be the max flow for that. I think it works. It doesn't, I mean, 3 plus 4 plus 4 is 11, 8 plus 3 is 11, so far so good. To B, 3 entered. And then 2 entered, so 5 entered, and 5 leave, so that's also correct. To C, 4 and 4, that's 8 leaves, so that's also fine. To D, you get 1 coming in, 1 going out. To E, you get 5 going in, 5 going, yeah, so this is the max flow output. So you just keep finding paths from here to there, and you keep updating. To each round, you shrink the edges here and increase the weights there. And once you no longer have paths from A to F, then this is finalized and the algorithm is done. I mean, if you just look at this drawing, it's not easy to see what the steps were, so that's why you have to practice yourself. And when I did this algorithm in class, I kept just drawing new graphs over and over instead of just doing everything in one graph. And it's easy to follow what's going on that way. But you could just keep updating your graph. And if you're careful enough, the output will be correct.
Professor, a couple things. Excuse me. During the exam, would you recommend doing multiple graphs, just updating one graph? If this was on the if Maxwell was on the exam.
I think that depends on the person. So obviously, if you just keep one graph, that's gonna be faster for you, right? So if the time is an issue, then you probably want to learn how to do it in just one graph. But if you just use one graph, it's also easier to mess up. Because if you keep drawing them, I mean, when something is 0, you just delete that edge, right? And now it's not there, and it's kind of easier to spot the new paths. So it also has an advantage to keep just updating the graph.
Yeah.
So again, over there, I did these 2 algorithms, right? I did this and that. I just used the same graph to do both. Yeah.
Can you do an example with the Huffman tree?
Huffman tree. Yeah. So this one. For this one, I will need to find an example. Okay, let's do this example. We have we have that information. We have 10 A's, 15 E's, 12 O's, 3 S's, 4 T's, 13 blanks, 1 new line. And we want to come up with a code for each letter. Okay. So let's put them in order. So NL is 1. S is 3. T is 4. A is 10. O is 12. BM is 13. And E is 15. Okay, so you grab the two smallest numbers, those are 1 and 3, and you get them together. And you add them. So now you forget about them. Now you look at the numbers left, the two smaller numbers are 4 and 4. So you join them. Okay. Now the two smallest numbers are 8 and 10, you join those. Now you grab the two smallest numbers, those are 12 and 13, you join those. Now you grab the two smallest numbers, those are 15 and 18, you join those. So let me just move this over here, just to make the joining easier. And then finally you join these two. Okay? So you have this tree. Let's see, so we have 58, 33, 25, 18, and E. The 25 breaks is O and BL. The 18 breaks is 8 and T. The 8 breaks is 4 and S and L. So you have this tree. These numbers are irrelevant. I'm just keeping them so that I can remember which ones are connected.
I think 18 goes to A.
Which one?
18 goes to A.
This?
Yeah. Oh, that's T.
The other way around?
Yeah.
Okay, so then you have this, and then you put numbers in each thing. And then you follow the paths. So to get from here to NL, you go 0, 0, 0, 0, 0. So NL will be 0, 0, 0, 0, 0. Then to get to S, you go 0, 0, 0, 0, 1. And to get to T, you go 0, 0, 0, 1. To get to A, you go 0, 0, 1. To get to E, you go 0, 1. To get to O, you do 1, 0. And to get to BL, you do 1, 1. And that's the output. It's not unique output. Right. You could pick whatever numbers you want on these ones, and it'll all work out. Although it's easier if you keep all the lefts be the same than all the rights. Yeah.
On the exam, do we have to make a cleaner graph like what's on the right, or can we just use the first one?
This?
Yeah.
Yeah, you can use this. I mean, what matters is this.
Oh, okay.
I just, to me, it's a little cleaner looking at it here than here, but of course, you could just put the zeros and ones here and figure it out. So you can just see that to get to NL, you did 0, 0, 0, 0, 0. So just tell 'em.
I think I missed this. Well, how do you determine which edges are zeros and ones?
I'm just going left is 0, right is 1. But it actually doesn't matter.
Oh,
If you make all the lefts ones and all the right zeros, it still
oh, you
works.
just have to choose one of those two options.
Yeah.
Okay.
I think, I'm not sure, but I think in each one of the decisions, you can make any of the, like, you could do 0, like here's gonna be 0, 1, here's gonna be 1, 0, here's gonna be 1, 0. You can make
Oh, for
any
each
choice
tree.
for each break,
Branch.
you can make any choice you want and it should work. So, yeah, so this will be annoying to grade because if you're just consistent with your write-up, any choice will work. So, I mean, how many possibilities are there here? 1, 2, 3, 4, 5, 6. So there's 64 different answers that are correct for this. So it's gonna be annoying to grade. Which gives you a hint that there's a big incentive for me not to put this in the exam. Yeah, it's like, I don't wanna grade this. So if I put it, just choose all zeros on the left and all ones on the right. It'll make my life easier. And also these problems are kind of easy to do, so you might want these on the exam. Although a lot of, I mean, the hardest of these is probably max floor, right?
Yeah.
Dijkstra is the next hardest. Floyd is hard to understand the notes, but I think if you're in class Monday, I think you would agree that it's easier than these two. And then topological sorting is also quite easy once you know what's going on. I mean, all you have to do is find the vertex that has the smallest, that has 0 in degree, and that's your next vertex to pick. So you just keep analyzing which one does not have anything going into it. That's the next vertex I'm gonna pick. So this is also an easy algorithm. Yes, sir.
Can you go over like a small example of Floyd one more time?
Of Floyd?
Yeah.
Yeah. Let's just again. Well, we could. I guess we could even use the one we drew. Well, that's not too small, but. Okay, let's do a small example. I don't know, let's do this. 5, 4, 3, 2, 1, 1. Okay. Okay, let's look at this example. And so the first, well, in the exam, I won't give you a diagram, I will give you a matrix. But let's pull the matrix from here. So the matrix is, so let's think of this as V1, V2, V3, V4, V5. Okay, so from 1 to 2, we get, so from 1 to, so these are all zeros. And from 1 to 2 is 5, from 1 to 3 is infinity. this example might be too simple. Okay, so let's say I give you this matrix and it asks you to find F5. Right? So you need to find F1, F2, F3, F4, F5, and so you need to do all the steps. So if you do it using the diagram, then so the diagonal entries stay the same. Yeah, this one's too easy. Alright, so the first guy stays the same. Alright, so then how do you do the second row? So basically you want to go from B to all the other guys, and you're allowed to use A. So it's not gonna help. Alright, now let's do from C to all the other guys, and we're allowed to use A. Yeah, I mean, it's kind of an issue because C is not connected to anything. And then D to all the other guys, and you're allowed to use A. Okay, this is not a great diagram because everything is going to stay the same. This last one here, yeah, because nothing, I don't have any arrows going backwards. So this problem's not too interesting. Okay, let's pick a different one. Let's add some back arrows. So let's do, here let's do a 2, so beta E. And let's also go back here. Beta A. And maybe let's connect C to E. Okay, so this is slightly more interesting. Let's do DB. Let's put a 1 format. DB. Alright, so we get this matrix. Okay, so the first matrix is just the adjacency matrix. You put the number, so if you're connecting the second vertex with the fourth vertex, you see what the weight is there. So second vertex to fourth, there's no edge there, so that's why you write infinity. So why is this guy a 1? That's because from the fifth vertex to the first vertex there is an edge of weight 1. That's why this is 1. Okay. So in the particular row and column, you look at the vertex represented by that row, the vertex represented by that column, and you see, is there an edge there? If there is an edge, is it in that direction? And then what's the value? So here, that's a 1, so you put a 1. Now, from B to A, there's no edge, so 2 comma 1 is infinity. So if there's no edge, you write infinity. And from a vertex to itself, you just automatically write 0, because you're distant 0 away from yourself. Alright, then F1 represents the paths that use that first vertex. Okay, so let me refill it. So the first row stays the same because the first row represent things that use the first vertex to begin with. So if you can use the first vertex, that doesn't add anything to you. Now, for the second row, in theory, from B to C, maybe there's a path going to A somehow, and then to C. There is no path, so this number stays the same. So from B to A is still infinity. From B to B is still 0. From B to C is 1. From B to D, you can't get there. And from B to E, you can't get there. Oh, you can, right? It's a 2. Okay, and then from C to A, you can't get there using A. From C to B, you can't get there using A. C to C is 0. C to D, you can't get there using A. And C to E stays this. So far, the 3 rows are the same as these 3 rows. All right. Now let's go from D. From D to A, there's no path. From D to B, there's a path. From D to C, there's a path. From D to D is 0. From D to E, there's no path. Okay, E to A is 1. E to B, no path. E to C, no path.
Wait, E to B, E to B to be done with 6.
Ah, thank you. Thank you. So you could go 1, then 5. Right. Thank you. So that's the only change, I think. Alright, so the only change from here to there is that to get from E to B, you could now use this path. Yeah.
You said on the exam we're given the matrix, right?
Yeah, you will be giving these numbers.
So how are we gonna, like, are we supposed to draw a graph then to figure out that
If you're gonna solve it this way, yeah. Obviously, you could also solve it the other way, where you just use the entries in the graph. So the path with the entries in the graph is that, so let's say this 6 here, and you don't have the diagram, so that 6, this would be F, what is it, 5, 2? So F152 is the minimum of F052, comma, okay, so it would be F510 plus F120. Alright? So what is F520? That's this number here, infinity. And what is F51? That's this number 1. And F12 is that number 5. So the minimum of infinity in 6 is 6. So, of course, if you do it this way, it's going to be super long because you have 25 entries to do. And then you do it again for the next matrix, and then again for the next matrix, and then again for the next matrix, right? So you would be doing 125 sums. So my recommendation is you translate it to a graph and then and if there's something in the graph that looks weird, then maybe you do that part in algebra just to check your work. So the next one is now you're allowed to use the first 2 vertices as intermediate steps. So this will not change at all. Well, maybe. Sorry, that's not true. That's just, be careful with what I say here. All right, so from A to A is the same. From A to B, that's the same. From A to C, now there's a path going A to B to C. From A to D, that there's the same path as before. And from A to E, there's 2 paths. One is this 3, the other one is 5 plus 2. 3 is less than 5 plus 2, so we keep the 3. And then from B to A, there's no path. From B to C, I mean, we're not gonna beat 1. From B to D, there's still no way, I think. from B to E. Still no way. Sorry, still just straight. What?
Is there a path to D?
There is no path where you use A.
Yeah.
So the path to D would be B, C, E, D, right? But that one you need intermediates C, D, and E, which you are not able to use yet. So for the final matrix, yeah. Okay, so then from C to A, still infinity. From C to B, still infinity. From C to 0. From C to D, still infinity. From C to E, still 3. From D to A, still infinity. From D to B, still 1. From D to C, still 1. From D to D, still 0. From D to E. Oh, from D to E, now there's a 3, right? So now we can do D, B, E. And then from E to A, 1. E to B, still 6. E to C. Oh, now there's a path because you can go A, B, C. So 1 plus 5 plus 1 is 7. E to D, I think there's no path except the one that was already there. And then E to E is gone. All right, so then we get this matrix. Then the third one is now you're allowed to use A, B, and C as your intermediate steps. And you build all of this guy. Then F4, you're allowed to use A, B, C, and D as your intermediate steps. And F5, you're allowed to use everything. But, I mean, I can keep going, but we have 4 minutes, so if you have other questions, maybe it's better to use it. Yeah.
For the coin change problem, could we be asked to prove if something is optimal, or the greedy is optimal?
It would be like a true-false. Like, the greedy is optimal with these coins. True or false. Any other questions? So Floyd, if I want to do it by hand, I think the bigger the matrix, the biggest matrix I could give you might be a 4x4. It's, I mean, as you can see, it's super time consuming, even with the graph as a tool. It's time consuming and it's easy to mess up. Now that one is one that it's one of the final projects if you want to pick that one. If you code it, what you would want to change is obviously
I'm gonna make the graph.
yeah.
I'm gonna visualize the graph and then build an AI to do the patterns for me.
Yeah, exactly.
It's gonna take 3 years to run. It's gonna take 3 years to run.
Yeah, it's just like the homework problem. Anything else you want to review? You ready?
No, this takes so long.
Okay, well good luck on midterm 3. I'll see you on Friday.